Last time, I gave you an introduction to dilution ventilation. Basically, what it is and how it works. How it differs from local exhaust ventilation. We talked about some advantages and disadvantages of dilution ventilation. One of the options that we have available to us if we need to use dilution ventilation is just to incorporate natural airflow. And that's what I want to talk about now, is natural ventilation of workspaces. In some workspaces, that's all that's needed. You can open some windows, open some doors, get a good cross ventilation going through your space, and that can provide all of the dilution air you need in many workplaces. An example of how much air is being moved by wind is what we have on the screen. A 15 mile per hour wind can move up to 20,000 cubic feet per minute through a 36 square foot opening. That's a lot of air movement through just a 36 square foot opening. That's a pretty big opening. That'd be 6 by 6 opening. But some workspaces have garage doors that can be opened, windows that can be opened, and that alone can be enough to dilute any contaminants in the workspace. And if you're wondering how we came up with a 15 mile per hour wind, 25,000 cubic feet per minute, there is the formula that you could use to do the calculation. You could do the calculation for 8 miles per hour or whatever wind you're dealing with. Again, if anybody's interested in the formula and the calculation, let me know. I can give you some more information. You're not required to do this calculation on the exam, but I just wanted to show you the formula that could be used to calculate the volume of airflow through a workspace based upon wind movement. The diagram here below, it just illustrates what we're talking about. You have wind pressure, a positive pressure blowing against a building, entering through an open window or door. Generally, where natural ventilation is used, there's going to be some type of venting on the roof that will allow the contaminated air to escape. Because, let's assume this workspace here has contaminated air. We have fresh air coming in. It's coming into the space, mixing with the contaminated air. As the air warms, it rises, and that contaminated air is going to be carried out through a gravity vent. A gravity vent means that there's no fan. There's nothing mechanical. There's nothing that has to be wired or powered. It's like the ventilation on the rooftop of a house that allows the hot air in an attic to dissipate out of the roof. Hot air rises, goes through these types of non-mechanical vents, and is dissipated into the outside atmosphere. Natural ventilation can be a function of wind currents, or can also be the function of temperature differentials. When we talk about temperature differentials, we're also talking about pressure differentials that make air move. Remember, it's all about pressure differentials, with high pressure flowing toward lower pressures. That's if you go on a really macro scale, that's how wind works. We have high pressure systems, low pressure systems. The air moves around the earth from high pressure systems to low pressure systems. And depending upon the strength of the particular high pressure or low pressure area, the winds can be stronger or lighter. But again, temperature and pressure are related. We didn't get into any of the ideal gas laws or any of the gas laws at all, but there's a relationship between pressure and temperature. Higher pressure is associated with higher temperatures, lower temperatures, lower pressures. Also, and this goes along with wind flow through a space, it also goes along with temperature differential, but we have what we call a chimney effect or a stack effect within structures, where air enters a structure and it rises, and as it heats, it rises and will be dissipated outside the building. Just like fire gases coming up through a chimney in your fireplace at home or your wood stove at home. Or if you don't have a fireplace or a wood stove, this same principle is incorporated into some other elements of most houses. Again, like the attic vents on homes, or it could be the exhaust fans out of bathrooms that have a flue attached to them, and that chimney effect plays a role there in removing those noxious gases out of bathroom facilities or kitchens. Yeah, natural ventilation can be an option. There are certain things that need to be considered if you're designing a structure for natural ventilation. You want to make sure to have plenty of openings that allow cross ventilation. You want intake openings, you want exhaust openings, and all four sides if possible. Now, if you end up going to work for a company and let's say they have a shop that doesn't have adequate openings, that might be a case you could make to your boss. Hey, maybe we cut in a door or a window on the north and south sides. We've got doors and windows on the east and west sides. Let's put some on the north and south sides. That way we can open these windows and provide a cross ventilation regardless of which direction the wind's coming from. Also, if you can, incorporate roof openings. Take advantage of that chimney effect and allow the dissipation of air that's heated and rises into the upper elevations within a workspace. Now, down below in the drawings here, the diagrams here are some examples. Now, single-sided ventilation, it can work, but it's better to have the cross ventilation like we see here. We have air blowing in one window and out the other. And ideally, your workspace is going to be in that airflow, in that airstream. Over here, furthest to the right, we have makeup air or supply air coming in through windows and being exhausted naturally through roof windows or skylights that open. That's a good design as well. But if you can, all four sides, openings on the roof to dissipate heat. But keep in mind, it's possible for air to move without adequate mixing or dilution of the air. If the air streams do not come into contact with where the contaminant is being generated, then the contaminant may not be diluted. To help overcome this potential problem, try to locate the workstations where the contaminant is generated in these air streams. Again, if over here you'd want your workstations in areas that are going to be downwind of the supply air and upwind of the exhaust air. Again, the single-sided ventilation, that's a little trickier. You would need, if all you had available to you was one window that you could open. You want to make sure to have continual monitoring going on within your space to make sure that adequate mixing and dilution is taking place. But really, that applies to all of these situations. Monitor your air continually. Yep, lift continually. Yep, that's that. I spelled it right. Trust me on that. I had to add my U, but I got it in there. Now, one thing, if you're building a new facility from scratch and you want to make sure you get the ventilation configured properly, hire an engineer. Get an engineer, get a designer involved, and there's going to be a designer and engineer involved if you're building a new facility. But make sure that they understand your interest in having good airflow through the facility. Again, if that's one of your goals, having good airflow for ventilating the area, make sure your engineer knows that, your designer knows that up front. And a lot of you will go into situations where the buildings are already built. Maybe they don't have adequate natural ventilation configured into the design. that's where you might, like I said previously, be able to make a case to your boss that if we did this or this, maybe we can improve airflow and we don't have to run the fans as much. If you can get the natural ventilation going, it can be a lot more cost effective for an operation. But there are situations where natural ventilation is not going to work for you, where you have to go with a mechanical ventilation system. And by mechanical ventilation system, I mean a system that has fans. It doesn't necessarily have to have all the ductwork and dampers and elbows and all those components. It doesn't have to have filtration systems. But mechanical ventilation, you'll be using fans to help move the air through the space. Here are some examples where mechanical ventilation would be needed, where natural ventilation is not going to be enough. And I left out a word. Okay, we're doing our testing, we're doing our monitoring, and we find that our natural ventilation is not effectively diluting the contaminants. Or maybe natural ventilation is not keeping the oxygen level at the proper, safe level for workers. And that's another thing to consider. Oxygen level, it's not just toxins. Also, the flammable vapors have to be considered also. But based upon your testing, if the natural ventilation is not doing the job, then you're going to need to consider mechanical ventilation. Or maybe you're in a situation where there's no wind to move air through the space. Maybe your building is in an area where natural airflows are blocked by other buildings or trees or other structures. Or maybe the workspace is inside a tank, inside a pit or an excavation where you can't get that natural cross ventilation going. That would be a situation where you would need mechanical ventilation. Or maybe you have an open window, but there's no exhaust outlet that's possible. You can't cut another window in, you can't put in a roof window, so you're not able to get good cross ventilation through the structure. If that's the case, you may need mechanical ventilation. Again, air coming in ideally is going to have a way out. Another situation where, and I don't have this on my slide, but another situation would be if you're hot or cold environments. I do address this later in our presentation and our discussion, but if you're in an area where air temperatures are 95 degrees plus, and that's what you have available as ventilation air through your workspace, that might not be suitable. You may run into other problems when you're bringing in 95, 100 degree air into your workspace. Natural ventilation is not going to work perhaps in those situations. Or maybe you work in an area where it's 15 degrees in the winter. Every day it's 15 degrees in the wintertime. You can't just open the windows in those environments and maintain the safety of your workers. That's a situation where you may need mechanical ventilation systems. Mechanical ventilation systems that will treat the makeup air. They either warm it or cool that makeup air as it enters the workspace. This is a kind of situation where you may need to consider mechanical ventilation. This was a job over in northwest Arkansas in the Rogers area. It's where New Hope Road, if you're familiar with that area, it's where New Hope Road and Interstate 49 cross there in Rogers. And this bridge design, the foundation for the bridge is in deep cast in place, steel reinforced concrete footings. To get to the depth we had to build a caisson using what's called sheet piling. Sheet piling. These are steel sheets driven into the earth. We drive in all these steel sheets, and then we excavate out inside of that steel sheet structure. Then once we get deep enough, we can go in and start building our reinforced concrete footings for the bridge. In this situation, you have the potential for poor airflow, not good adequate natural ventilation. So first of all, you need to monitor. You have continual monitoring in this space. If you have any point source contaminants, you may need to use local exhaust ventilation. For example, if you have carbon monoxide from machinery, if you have vapors coming off your form release oil or your curing compound, the gasoline and the diesel, you may have fuel cans inside the space that are off-gassing. These situations, you may even need local exhaust ventilation. But as I've said before, what I've encountered in these situations is oxygen deficiency is most likely going to be your hazard. Not so much in this space. That's a pretty large space there. But if a little fresh air can get into this space and get the air moving and the chimney effect going, that may be all you need in a situation like this. Now, where I've had the bigger problems is when they're deep drilled shafts into the ground. 50, 60, 80 feet deep holes or pits straight down into the ground, and then you have to put workers down in there. That's where you're really going to have problems with oxygen deficiency. You absolutely have to have continual monitoring in that environment. The next slide here, we have a setup where we're using fans to blow fresh air into the space at all times. We're blowing that fresh air in. It's getting the air moving. We have a chimney effect in this space that's taking out the potentially contaminated air. We never had a personal monitor go off. We never got an alarm from any of the personal monitors that were being worn by workers in any of these sites. So our ventilation was working well. Now the fan here that you see, this is called a turbine axial fan. And it's really designed for providing temporary ventilation in workspaces like this. You can set it up either to blow air or you can set it up to exhaust air. All you have to do is turn the fan around. And the collapsible ductwork that we're using here, if you need it to, it's set up in a blowing configuration now, but if you wanted to set it up to remove air from the space, you just turn the fan around and hook up your ductwork, your flexible ductwork, and you're good to go. And another thing to remember, do not place your makeup air fan in an area where contaminants are generated. You wouldn't want to put your fan here right up next to a water pump that was pumping out carbon monoxide. If you do, there's a chance that you're going to pump carbon monoxide into your hole, which is not a good thing. All right, I'm going to go ahead and stop this module here. When we come back, we'll continue talking about dilution ventilation.